Every major moon in the solar system follows the same rule. They orbit in the same direction their planet spins, every one of them except one. Its name is Triton, Neptune's largest moon. More than 4.5 billion years old, it is moving backward, not because its orbit tilted over time, not because something nudged it slightly off course, because it was never supposed to be there. Triton is larger than Pluto, stretching 2,710 kilometers across, making it bigger than every known dwarf planet. Yet everything about it says it belongs somewhere else. It circles Neptune in the wrong direction. It formed far beyond Neptune's orbit. It is the coldest surface ever measured in the solar system, reaching roughly minus 235 degrees Celsius. And somehow, despite that unimaginable cold, it erupts. Towering plumes of nitrogen rise kilometers above its frozen landscape, driven by processes scientists are still trying to understand. Then there is something even stranger. Triton is already dying. Its orbit is shrinking, almost imperceptibly, carrying it closer to Neptune with every passing year. One day, billions of years from now, it will cross a point of no return. It will either crash into the planet that captured it, or be torn apart by gravity, transforming into a spectacular ring system unlike anything the solar system has ever seen. Everything about Triton's existence points to a violent past. It did not grow beside Neptune. It lived an entirely different life before a catastrophic encounter tore it away from its original home, reshaped Neptune's entire moon system, and imprisoned it in the orbit we see today. Humanity has visited this extraordinary world only once. Voyager 2 swept past Triton in 1989. The encounter lasted only a few hours and photographed just 40% of its surface. Everything we have learned since has come from mathematics, physics, and careful inference. This channel grows because of people who take a moment to like and subscribe. If you're one of them, thank you. It means we get to keep doing this. The story begins with the single rule every major moon is expected to follow, and the one remarkable world that never did. Imagine the earliest moments of a planet's life, long before oceans, mountains, or moons existed. Around a newborn world, a vast cloud of gas and dust slowly gathered into a broad spinning disk. Every grain joined the same graceful motion. As the cloud contracted under gravity, its rotation naturally increased. This follows the conservation of angular momentum, the principle stating that a spinning system preserves its rotational motion as its size changes. The shrinking cloud spun faster, and everything forming within that disk inherited the same direction. That shared motion shaped every large moon born there. Each one emerged from the same rotating material as its parent planet, growing through countless gentle collisions until gravity molded it into a nearly spherical world. Their paths reflected their birthplace. They traveled around their planet in the very same direction the planet itself rotated. There was no preference involved. There was simply physics, unfolding exactly as expected. We can see this pattern across the solar system. Our own moon circles Earth, while Earth spins beneath it in the same rotational sense. Around Jupiter, the great family of Io, Europa, Ganymede, and Callisto follows that identical rule, tracing orderly paths established billions of years ago. Saturn's immense moon Titan does the same. So do the major moons surrounding Uranus. Different planets, different environments, yet one remarkably consistent result. The pattern never changes. But nature does allow a few unusual companions. Far beyond the regular moon systems drift scattered captured objects, small fragments that once wandered independently before gravity claimed them. Some travel in reverse. They often follow distant, tilted, elongated paths, carrying the marks of chaotic histories. Yet these bodies remain small, irregular, and unlike the great rounded worlds formed beside their planets. You will not find a large, geologically active moon among them, moving backward through a stable orbit. That absence is every bit as important as the rule itself. Now we arrive at Neptune. It circles the Sun at roughly 30 astronomical units, one astronomical unit being the average distance between Earth and the Sun. That places Neptune about 4.5 billion kilometers from our star, which is about 2.8 miles. Even at that immense distance, it possesses a surprisingly rich family of companions. Today, astronomers recognize 16 known moons around Neptune, yet almost all of the mass belonging to that entire collection resides in one object alone. Triton accounts for more than 99.5% of everything orbiting the planet. The remaining moons are tiny beside it, almost like scattered fragments accompanying a single dominant world. Keep that picture in your thoughts as we continue together. Every large moon should reveal its birthplace through the direction of its orbit. Every major satellite around the giant planets confirms that expectation. Every piece of the framework now rests before us. Only then can we appreciate how extraordinary it becomes when one world refuses to follow the pattern at all. Long before Neptune ever held Triton in its grasp, this world already carried a history of its own. You can almost picture it traveling through a distant population of icy bodies, circling the sun with countless neighbors that shared the same remote frontier. Its present orbit tells only the latest chapter. Its deeper identity survives in the evidence locked beneath layers of ancient ice. Size offers our first clue. Triton measures about 2,710 kilometers across, which is about 1,684 miles. That makes it larger than Pluto and larger than every confirmed dwarf planet known today. It also ranks as the seventh largest moon in the entire solar system. Remarkably, its mass exceeds the combined mass of everything in the asteroid belt by a comfortable margin. This was never a minor object drifting unnoticed through space. But dimensions alone cannot reveal a birthplace. Chemistry can. Across Triton's frozen surface, roughly 55% consists of nitrogen ice, accompanied mainly by water ice and carbon dioxide. Smaller amounts of methane and carbon monoxide appear as well, identified through spectroscopy, a technique that studies how materials absorb and reflect different wavelengths of light. Each frozen ingredient leaves behind its own unmistakable fingerprint. Those fingerprints look strikingly familiar. Pluto displays frozen nitrogen, water ice, methane, and carbon monoxide across its surface. Triton presents the same collection in almost the same proportions. The resemblance reaches far beyond coincidence. You and I are looking at two worlds that appear to have grown within the same distant neighborhood, shaped from remarkably similar building blocks before their histories separated. Another clue lies deep inside. Triton's average density measures about 2.061 grams per cubic centimeter, greater than any other measured moon orbiting the outer giant planets. Higher density suggests a larger fraction of rock hidden beneath the ice. That rocky interior matches expectations for objects born in the Kuiper Belt, where material condensed under conditions unlike those surrounding the giant planets during their formation. The Kuiper Belt stretches outward from roughly 30 astronomical units to about 50 astronomical units from the Sun. It is a broad region filled with hundreds of thousands of icy worlds and smaller fragments. Pluto lives there, Eris lives there, Makemake and Haumea belong there as well. During the solar system's earliest ages, This distant realm contained even more objects, moving through a far busier and more dynamic environment than we see today. Everything points back to that forgotten frontier. Triton formed there as an independent world, circling the sun in the same direction as its countless neighbors for hundreds of millions of years. It belonged to no planet. Its landscape evolved beneath the faint sunlight reaching the outer solar system, untouched by Neptune's immense gravity. But every piece of evidence we have gathered, from its composition to its internal structure, leads toward the same conclusion. Triton began life as a Kuiper Belt world, carrying the unmistakable signature of a place far beyond the planet it circles today. Gravity is remarkably good at changing direction. Holding on is much harder. If you and I watch a wandering world pass close to a planet, the planet's gravity bends its path into a graceful curve, then releases it once more. Unless something removes energy from that passing object, it departs carrying almost the same total energy with which it arrived. Celestial mechanics, the mathematics describing motion under gravity, leaves very little room for exceptions. That creates a difficult puzzle. A free world cannot simply drift past Neptune and remain there forever. Some process must reduce its orbital energy enough for escape to become impossible. Without that missing step, every close encounter ends the same way. The traveler continues around the sun, and the planet watches it disappear into the distance once again. But researchers have developed a compelling answer. In 2006, Craig Agnor and Douglas Hamilton presented the leading explanation, known as the binary capture mechanism. A binary system is simply a pair of worlds orbiting one another while together orbiting the Sunday. We already know such arrangements exist throughout the Kuiper Belt. Pluto and Charon provide the most familiar example, although many smaller pairs have also been discovered beyond Neptune. Their proposal begins with Triton sharing space with a companion of its own. Rather than traveling alone, Triton circled another icy world as both slowly crossed the outer solar system together. Then came a close approach to Neptune. The giant planet did not pull equally on each member of the pair. Gravity weakened with distance, so the nearer object experienced a stronger attraction than the farther one. That uneven pull, called a tidal interaction because gravity stretches across distance, destabilized the partnership. Everything changed within moments. One member of the binary received extra orbital energy during the encounter and accelerated away. It may have escaped Neptune forever. It may even have gained enough speed to leave the solar system entirely, or perhaps it returned to the distant Kuiper Belt on a path we have never identified. No observation has revealed its fate. Triton paid the opposite price. As its companion gained energy, Triton lost the same amount through the gravitational exchange. That reduction slowed it enough to fall below Neptune's escape velocity, the minimum speed required to break free from a planet's gravitational pull. From that instant onward, Neptune no longer deflected a passing visitor. It possessed a new moon. The missing companion remains one of the most intriguing ghosts in planetary science. It may have been comparable in size to some of Neptune's smaller moons, yet today it has no confirmed identity. Perhaps it still wanders beyond the known frontier, or perhaps it has already crossed into interstellar space, forever separated from the world it once accompanied. But other ideas continue to receive careful study. Some researchers suggest drag from a young disk of gas and debris surrounding Neptune gradually removed enough energy for capture. Others explore whether a collision with an existing moon could have produced the same result. Those possibilities remain under discussion. One conclusion does not. Triton's backward orbit preserves unmistakable evidence that this remarkable world began somewhere else. A captured world does not settle into its new home overnight. Instead, its first journeys around Neptune would have traced an immense, elongated path, carrying Triton close to the giant planet before flinging it far back into space again. Each circuit crossed regions where other moons once traveled. Nothing about that early orbit resembled the graceful track we would recognize today. But elongated orbits rarely remain unchanged around a massive planet. Whenever Triton swept inward, Neptune pulled more strongly on the hemisphere facing the planet than on the hemisphere facing away. That unequal pull is called a tidal force, meaning gravity acts with slightly different strength across the width of an object. The difference was small at any single moment. Repeated endlessly, it became transformative. Each close passage gently squeezed and stretched Triton's interior. Rock shifted, ice flexed, hidden layers bent under stress, then relaxed again as the moon moved outward. You can picture a metal bar warming after being bent back and forth many times. The same physical idea applied here, although on a scale beyond imagination. Mechanical motion gradually became heat, buried far beneath the frozen surface. That energy came from somewhere. It came from Triton's orbit itself. Every cycle transferred a tiny amount of orbital energy into the moon's interior, leaving the orbit slightly less stretched than before. Hundreds of millions of years passed, perhaps more than 1 billion years. Little by little, the long ellipse contracted until Triton settled into one of the most circular paths known for any moon in the solar system. Its orbital eccentricity, the measurement describing how stretched an orbit remains, is now almost zero. But another captured moon reminds us that this outcome was never guaranteed. Saturn's moon Phoebe also arrived from elsewhere, yet its orbital eccentricity remains about 0.16. Its path still carries the unmistakable signature of an unsettled past. Phoebe escaped the prolonged tidal reshaping that transformed Triton so completely. We can still read its history directly from its orbit. The amount of heat generated inside Triton during this immense period may have rivaled the tidal heating experienced by Io, the innermost large moon of Jupiter and the most volcanically active world currently known. Yet Triton's transformation unfolded across a much longer span of time. The process continued patiently as orbit after orbit surrendered another small measure of energy to the interior. Nothing inside remained untouched. Dense rock gradually settled downward, while lighter, icy material rose above it. Internal layers became increasingly organized under the influence of gravity and heat. The moon that Neptune captured slowly turned into a different kind of world altogether. But this explains something that once seemed deeply puzzling. Triton's unusual geology did not simply appear by chance. The activity that would later shape its frozen landscape was forged through this prolonged gravitational struggle. Neptune did far more than capture an outsider. Over immense stretches of time, the planet reshaped Triton from its deepest interior outward, leaving behind a world whose history became permanently written into its structure. The deepest changes happened far below the frozen ground, where no camera has ever looked. Everything we have discussed about Triton's violent past left a lasting imprint beneath its surface, preserving a structure that scientists can reconstruct through physics rather than direct observation. Piece by piece, that hidden architecture reveals a world far more complex than a simple mixture of ice and rock. Planetary scientists describe Triton as differentiated. The word simply means that gravity has sorted the interior into separate layers according to density. Heavier material gradually sank toward the center, while lighter material rose above it. Earth formed this way, with dense metal concentrated deep inside, rocky layers resting above, and a comparatively thin outer crust covering everything. Triton appears to have followed the same fundamental process, despite its very different history. Current models place a dense, rocky, and metallic core at the center, containing roughly two-thirds of the Moon's total mass. Surrounding that core lies a mantle composed mainly of silicate rock, minerals built from silicon and oxygen that make up much of Earth's own crust and mantle. Above the rocky interior rest thick layers of water ice. Finally, the outermost shell consists largely of frozen nitrogen, together with methane and carbon dioxide coating the surface we would eventually observe. Such orderly layering demands a tremendous source of heat. Solid material cannot separate itself by density unless it becomes soft enough for gravity to rearrange it over immense spans of time. On Earth, that energy came largely from the violence of planetary formation and the continuing decay of naturally radioactive elements. Triton followed another path. The prolonged tidal heating produced after capture supplied much of the energy needed to reshape its interior from within. But one possibility reaches even deeper. Could liquid water still exist beneath those frozen layers today? That question has become one of the most compelling areas of Triton research because several independent lines of evidence suggest the answer may be yes. Computer models combine three important heat sources. The first is lingering warmth left behind by the ancient tidal heating episode. The second comes from radiogenic heating, the slow release of energy as radioactive elements inside the rocky core naturally decay over billions of years. The third involves dissolved ammonia or salts mixed into underground water. These substances act like antifreeze, lowering the freezing temperature and allowing liquid water to persist under conditions where pure water would already be solid ice. Research published during 2024 in the Planetary Science Journal concluded that a long-lasting subsurface ocean, together with an extended period beneath a comparatively thin ice shell, would greatly strengthen Triton's potential as an environment worthy of astrobiological investigation, the scientific search for conditions that could support life beyond Earth. But no hidden ocean has yet been confirmed. Detecting one requires instruments capable of probing the unseen interior, including magnetometers that measure magnetic fields, gravity experiments that reveal hidden mass distributions, and seismometers that record vibrations traveling through the Moon. No spacecraft has ever carried those tools to Triton. Even so, the possibility has advanced beyond simple imagination. Today, it stands as a serious scientific hypothesis, waiting for observations that only a future mission can provide. For generations, Triton existed as little more than a distant point of light drifting beside Neptune. Through even the finest telescopes of the 19th century, you could never make out mountains, plains, or frozen landscapes. There was only a faint companion accompanying the outermost giant planet, offering almost nothing about its true nature to anyone watching from Earth. Its discoverer was an unlikely figure. William Lassell earned his living as a brewer, yet devoted his personal fortune to building powerful telescopes with his own hands. After Neptune itself was identified in October of 1846, the astronomer John Herschel encouraged Lassell to search for accompanying moons. He accepted the challenge. Only 8 days later, and just 17 days after Neptune's own discovery, Lassell found Triton through observations made from Liverpool. A remarkable beginning, but discovery did not bring understanding. During the following 143 years, astronomers could measure Triton's orbit, estimate its distance from Neptune, and calculate an approximate mass. They could not examine its surface. They could not study its atmosphere. Its geology remained completely beyond reach. hidden by distance and limited technology. Everything changed on the 20th of August, 1977. The National Aeronautics and Space Administration launched Voyager 2, a robotic spacecraft built to take advantage of an extraordinary planetary alignment occurring only about once every 176 years. By using gravity assists, a technique in which a spacecraft gains speed by passing close to a planet, one mission could continue onward from one giant planet to the next without carrying impossible amounts of fuel. The journey unfolded across more than a decade. Jupiter welcomed the spacecraft in 1979. Saturn followed in 1981. Uranus came next in 1986. Finally, Neptune awaited in 1989. Each encounter reshaped the spacecraft's path, with planetary gravity bending its course toward the next destination. But reaching Triton demanded a difficult choice. Mission planners designed a trajectory that carried Voyager 2 close enough for detailed observations of the Moon, using Neptune's gravity to redirect the spacecraft downward across Triton's orbit. That decision came with a price. Entering orbit around Neptune became impossible. There would be only one passage through the system. On the 25th of August, 1989, at 10 minutes past 9 in Coordinated Universal Time, Voyager 2 reached its closest approach to Triton. It swept past roughly 40,000 kilometers above the surface, that is nearly 24,855 miles, while racing at about 15 kilometers each second, which is about 9.3 miles each second. The closest observations lasted only a few precious hours. But even then, the encounter remained incomplete. The geometry of sunlight illuminated only Triton's southern hemisphere. Most of the northern hemisphere stayed beyond detailed view, leaving roughly 60% of the Moon unmapped at close range. Voyager 2 has since crossed the heliopause, the boundary where the Sun's outward flowing particles give way to interstellar space. It will never return. Everything you and I know from nearby observations of Triton still comes from those brief hours during 1989. One measurement from Voyager 2 immediately overturned decades of expectation. Instruments recorded a surface temperature of minus 235 degrees Celsius, or minus 391 degrees Fahrenheit. That is only 38 degrees above absolute zero, the theoretical limit where molecular motion reaches its lowest possible state. Few places anywhere in the known solar system approach such extraordinary cold. To appreciate that number, it helps to compare it with something familiar to modern industry. Liquid nitrogen boils at minus 196 degrees Celsius or minus 321 degrees Fahrenheit. It demands specialized equipment on Earth because direct contact causes severe frostbite within moments. Triton is another 39 degrees colder than that boiling point. Nitrogen, the gas making up roughly 78% of Earth's atmosphere, does not remain a gas there. It freezes into solid ice across the landscape. Everything about planetary science suggested that such a world should be geologically inactive. Extreme cold slows physical processes, reducing the energy available to reshape a surface. We would expect ancient terrain, preserved almost unchanged across immense spans of time. The prediction seemed straightforward. Then Voyager 2 transmitted its images. But rising above Triton's southern polar cap were towering dark columns reaching about 8 kilometers into the sky, which is about 5 miles. Strong winds high above the surface caught those columns and carried their material sideways for more than 150 kilometers, which is about 93 miles, painting long dark streaks across the brilliant frost. The spacecraft documented at least 4 active geysers during its brief encounter. Two became especially important because scientists observed them in greater detail. They received the names Hili, honoring a water spirit from Zulu tradition, and Mahalani, named after a sea spirit from Tongan tradition. Those names remain attached to some of the most remarkable eruptions ever observed beyond Earth. Each plume formed a remarkably slender column, ranging from only a few tens of meters, which is about a few tens of feet, to perhaps 1 kilometer across, that is nearly zero point 0.6 miles. The eruptions carried nitrogen gas mixed with extremely fine dust. As winds transported that material across the frozen plains, it settled into long surface markings that Voyager 2 photographed with astonishing clarity. Scientists counted well over 120 of those dark streaks spread across the southern polar region. Every streak marked the path of material carried away from an eruption. Some appeared relatively recent. Others had persisted much longer, remaining visible against the pale surface because the surrounding frost preserved them so effectively. Individual geysers may continue erupting for as long as a year. Researchers estimate that a single event can vaporize roughly 100 million cubic meters of frozen nitrogen. Imagine a cube measuring about 465 meters on every side, which is about 1,526 feet. That enormous volume can ultimately be transformed into gas and lofted skyward. But perhaps the greatest surprise was not the height of the plumes or the amount of material they released. It was their existence at all. On the coldest measured surface in the solar system, where every expectation favored geological stillness, Voyager 2 found unmistakable signs that Triton remained astonishingly active. Some discoveries become even more fascinating after the first surprise fades. The towering plumes on Triton belong in that category. We now know they exist, yet the deeper mystery has shifted toward a different question. What is actually driving them? The answer determines whether we are watching a remarkable surface phenomenon or witnessing evidence of activity rising from deep within an alien world. The first explanation begins with the faint sunlight reaching Neptune's distant realm. Triton orbits about 30 astronomical units from the Sun, placing it roughly 4.5 billion kilometers away, which is about 2.8 billion miles. Even there, a small amount of solar energy still reaches the frozen surface. It is weak, yet it never falls completely to zero. According to the leading surface model, that sunlight passes through a translucent layer of nitrogen ice before reaching darker material buried just beneath it. Those darker grains absorb more energy than the bright ice above them. The warming may amount to only a tiny fraction of a degree, but under Triton's unusual conditions, even that slight increase can vaporize nitrogen trapped below the surface. Pressure slowly builds until the overlying ice finally fractures, releasing gas and dust upward in a powerful eruption. Under this explanation, the geysers are controlled mainly by the seasons and by sunlight. They should appear most readily where the sun shines directly overhead. That prediction agrees remarkably well with Voyager 2's observations during the flyby, since the documented plumes clustered near the region, receiving the greatest solar illumination at the time. But another possibility reaches far below the surface. Scientists describe it as endogenic activity, meaning geological processes powered by internal heat rather than external sunlight. In this picture, lingering warmth from Triton's ancient tidal heating, together with continuing radiogenic heating from naturally radioactive material inside the rocky core, supplies enough energy to vaporize buried nitrogen from below. The plumes become expressions of an active interior instead of seasonal surface warming. That distinction carries extraordinary consequences. During 2022, research led by Hofgartner and colleagues concluded that an internal origin for the observed plumes could not be ruled out using the available Voyager 2 measurements. The existing evidence simply does not eliminate that possibility. If sunlight alone drives the eruptions, then the geysers reveal an elegant story about frozen surfaces responding to changing illumination. But if internal heat powers them instead, every eruption could be transporting material upward from much deeper levels. Hidden water, dissolved minerals, and complex chemical compounds might eventually reach the surface through these natural pathways. Imagine what that could mean for exploration. Rather than drilling through kilometers of solid ice, which is about miles of frozen crust, a spacecraft could potentially fly directly through an active plume and sample material originating far below the surface. The chemistry of a concealed interior might become accessible with a single, carefully planned pass. For now, we cannot tell which explanation is correct. Voyager 2 gathered far too little information during its brief encounter to separate one model from the other. That unresolved question remains among the highest scientific priorities for any future mission returning to Triton. Every crater tells a story. Across the solar system, those stories accumulate until they become an archive written into stone. Our own moon preserves impacts dating back billions of years. Mercury remains densely covered by ancient collisions. Mars still bears scars from objects that struck long before life appeared on Earth. Even the icy moons orbiting Jupiter and Saturn carry records of countless encounters stretching back almost 4.5 billion years. Time rarely erases such marks, but Triton refuses to preserve them. Its surface contains remarkably few impact craters, and that absence speaks more loudly than their presence ever could. Craters certainly formed there, just as they did across the rest of the solar system. Yet something repeatedly removed them. The evidence points toward a landscape that continually renews itself, replacing older terrain with fresher material before the accumulated history can remain visible for very long. That gives Triton a geologically young appearance, despite its immense age. The moon itself formed billions of years ago. The face presented to space is much younger, refreshed again and again through ongoing geological processes that slowly overwrite what came before. One mechanism involves the steady migration of volatile materials, substances that easily change between solid and gas under Triton's conditions. Nitrogen and methane freeze onto the winter pole, then gradually return to gas as sunlight reaches the opposite hemisphere. During Triton's approximately 41-year seasonal cycle, those materials travel from one pole to the other, settling as fresh frost that blankets older landscapes beneath successive layers of ice. But this migration may influence the moon in another remarkable way. As enormous amounts of frozen material shift across the surface over periods approaching 10,000 years, the distribution of mass slowly changes. Planetary scientists propose that these changes can cause true polar wander, a process in which the outer shell gradually reorients relative to the interior. Triton's geographic poles may therefore drift over immense spans of time, instead of remaining permanently fixed. Another clue appeared before Voyager 2 ever arrived. Observations made during 1977 showed Triton with a noticeably reddish coloration resembling Pluto. By the time Voyager reached Neptune in 1989, much of that reddish appearance had faded beneath newly deposited nitrogen frost. Older reddish tholins, complex organic molecules created when radiation alters nitrogen and methane, had become hidden beneath brighter frozen deposits. Even the moon's color had changed within little more than a decade. But the most powerful resurfacing process almost certainly comes from cryovolcanism. Unlike familiar volcanoes on Earth, cryovolcanoes erupt water, slushy mixtures, or volatile compounds instead of molten rock. Those materials spread across the landscape before freezing into broad, smooth plains. Vast regions known as Tuonela planitia and Ruach planitia appear to preserve exactly this history, their remarkably level surfaces suggesting ancient floods of icy material that hardened into place. On Triton, the landscape does not simply endure, it continuously rewrites itself. Some discoveries answer long standing questions, others create entirely new ones. Among everything revealed during Voyager 2's brief encounter with Triton, one landscape stood apart so completely that planetary scientists struggled even to describe it. Eventually, they borrowed a comparison from everyday life. They called it cantaloupe terrain because its repeating pattern resembled the textured skin of a cantaloupe melon. The name sounds ordinary. The geology behind it is anything but. This remarkable landscape stretches across much of Triton's western hemisphere. Instead of sharp mountains or heavily cratered plains, you find countless rounded depressions arranged in an intricate repeating pattern. Most measure between 30 kilometers and 40 kilometers across, which is about 19 to 25 miles. Narrow ridges separate neighboring hollows, while long troughs weave through the region, producing a surface that appears almost organic when viewed from orbit. But appearances can be misleading. Impact craters follow no preferred size. Larger objects create larger scars, while smaller objects leave smaller marks, producing an irregular distribution across any ancient world. Triton's rounded depressions refuse to follow that rule. Their dimensions remain strikingly consistent, their shapes remarkably alike, and their arrangement suggests a common internal process rather than countless random collisions arriving from space. The leading explanation centers on diaporism, a geological process in which warmer, less dense material slowly rises through heavier layers above it. You can picture wax drifting upward inside a slowly heated lava lamp, although Triton's version unfolds over immense spans of geological time. Beneath the frozen surface, warmer ice may have become buoyant enough to push upward through colder, denser ice. As those rising masses distorted the crust, they produced the repeating domes, depressions, and ridges that Voyager recorded during its single flyby. But another detail makes the puzzle even more compelling. Long, paired fractures slice across parts of the cantaloupe terrain, running side by side for great distances before fading into neighboring landscapes. Similar double ridges appear on Europa, one of Jupiter's largest moons, where many researchers suspect a global ocean lies beneath an icy shell. Although the two worlds followed dramatically different histories, the resemblance encourages scientists to ask whether comparable internal forces may have shaped both surfaces from below. Evidence also suggests that the cantaloupe terrain represents some of Triton's oldest exposed landscape. Despite enduring immense stretches of time, it remains recognizable beneath later modifications. That persistence hints that the underlying structures originated deep inside the moon rather than forming through temporary surface deposits or seasonal frost. They are rooted within Triton's interior architecture itself. As of 2026, no other known world displays terrain quite like this. Not Earth, not Mars, not Pluto, not any moon circling the giant planets. Whether this extraordinary landscape records Triton's unusual capture, its prolonged tidal heating, or an entirely unfamiliar geological process remains uncertain. We simply know that nowhere else in the known solar system has nature written the same pattern twice. Sometimes the most surprising feature of a distant world is something you would never expect to find at all. Around Triton, beyond its frozen plains and active surface, there exists an atmosphere. It is not merely a scattering of stray particles drifting into space. It is a genuine atmosphere, structured, measurable, and constantly changing as the seasons unfold across this captured world. Its pressure at the surface measures about 14 microbars, roughly 1/70,000th of the atmospheric pressure experienced at sea level on Earth. That value is extraordinarily small. If you could somehow stand upon Triton, you would experience conditions that felt almost indistinguishable from empty space. Yet instruments can still detect this fragile envelope, allowing scientists to calculate its behavior and follow its evolution through careful observation. The atmosphere closely reflects the chemistry already frozen across the landscape below. Nitrogen forms nearly all of it. Small amounts of methane and carbon monoxide are also present, matching the same volatile combination found across Pluto. This correspondence reaches beyond coincidence. It strengthens the growing picture that both worlds began their histories in the distant Kuiper Belt before their paths ultimately diverged. But even an atmosphere this thin remains surprisingly active. Under the faint sunlight reaching Neptune's realm, tiny particles of frozen nitrogen may condense into delicate clouds several kilometers above the surface, which is about several miles depending on their altitude. These clouds represent genuine weather, unfolding in conditions colder than anywhere else yet measured within the solar system. Winds also move through this rarefied air, carrying suspended material across remarkable distances despite the atmosphere's extreme delicacy. Its greatest surprise lies elsewhere. Observations gathered after the Voyager 2 encounter revealed that Triton's atmospheric pressure has not remained constant. Instead, it has varied by as much as a factor of 3 over only a few decades. Within planetary science, where many changes require millions of years to unfold, such variation is astonishingly rapid. The atmosphere breathes with the seasons, expanding and contracting as frozen gases repeatedly exchange places between the ground and the sky. The explanation rests in Triton's unusual orientation around Neptune. Its orbital plane is tilted by about 157 degrees relative to Neptune's equator, allowing each pole to experience prolonged sunlight followed by equally prolonged darkness during a seasonal cycle lasting about 41 years. As the southern hemisphere entered deeper summer after the Voyager 2 flyby, increasing sunlight transformed more nitrogen ice directly into gas through sublimation, meaning solid material changed directly into vapor without first becoming liquid. The atmosphere gradually became denser as additional nitrogen entered the air. But this expansion cannot continue forever. Eventually, the seasons will reverse. Sunlight will fade from the southern pole. Nitrogen will freeze onto the surface once again, and the atmosphere will slowly contract. Throughout that cycle, upper atmospheric winds continue carrying dust from Triton's towering geysers for more than 150 kilometers, which is about 93 miles, painting long dark streaks across fresh frost and quietly reshaping the appearance of an already extraordinary world. Long before Triton settled into the orbit we recognize today, Neptune almost certainly possessed a very different family of companions. Like the other giant planets, it would have gathered moons from the broad disk of gas, dust, and ice surrounding it during its formation. Those original satellites would have circled in the same direction as Neptune's rotation, moving through stable paths that had endured for hundreds of millions of years. Their system reflected the ordinary outcome of planetary formation. But ordinary did not last. When Triton arrived, it was not entering empty space. Its newly captured orbit was highly elongated, carrying it close to Neptune before sweeping far outward again. During every circuit, Triton repeatedly crossed the regions occupied by those earlier moons. Each passage created opportunities for powerful gravitational encounters. Sometimes the moons passed at a distance, sometimes they approached much more closely. Over countless orbits, those repeated interactions steadily unraveled the architecture of Neptune's original satellite system. Some moons gained enough energy to escape Neptune altogether, leaving behind the planet that had once held them. Others spiraled inward until they crossed the Roche limit, the distance where a planet's tidal forces become stronger than a moon's own gravity and can pull it apart. Once disrupted, those shattered bodies spread into expanding clouds of debris that gradually circled Neptune as broad rings of broken rock and ice. The destruction did not mark the end of moon formation. Over time, material within those debris disks collided, merged, and slowly assembled into new satellites. The inner moons we observe today, including Proteus, Despina, Galatea, Thalassa, Naiad, and Larissa, are widely thought to belong to this later generation. Rather than preserving Neptune's original family, they may represent the survivors of an entirely different beginning, built from fragments left behind after the earlier system collapsed. One object preserves especially strong evidence of that violent transition. Nereid follows one of the most elongated known moon orbits in the solar system. Its orbital eccentricity measures about 0.75, meaning its distance from Neptune changes dramatically during every revolution. Such an extreme path suggests a profound disturbance in its past. Many researchers consider Nereid a likely survivor from Neptune's original collection of moons, scattered into its present orbit as Triton's repeated gravitational encounters transformed the surrounding system. But computer simulations strengthen that picture even further. Research published in 2009 by Robin Canup and Raluca Rufu examined how debris produced during Triton's capture could evolve around Neptune. Their models showed that the arrival of a massive retrograde moon could destroy the native satellites while naturally creating the debris required to build the smaller moons seen today. Triton's capture therefore reshaped far more than its own destiny. A single wandering world entered Neptune's domain, and an entire planetary family was broken apart before another slowly emerged from the remains. Some consequences unfold so gradually that no single moment reveals their scale. We can watch collisions, eruptions, and impacts in our imagination, yet the slow turning of an entire planet belongs to a different rhythm. Triton's arrival may have begun another transformation, one written into Neptune itself rather than the space surrounding it. Today, Neptune's axis leans by about 28 degrees relative to the plane of its journey around the Sunday. That inclination gives the distant planet seasons, much as Earth's tilt shapes the changing pattern of sunlight across our own world. For many planets, astronomers explain such tilts through giant impacts during the earliest stages of planetary formation, when young worlds frequently collided with one another. Uranus, leaning by about 98 degrees, remains the classic example of that process. But Neptune presents a different puzzle. No convincing impact scenario has fully explained why its axis settled into its present orientation. The available evidence has long encouraged scientists to search for another mechanism, one capable of changing a planet's rotation without requiring a catastrophic collision. That search recently produced an unexpected possibility, placing Triton at the center of the story once again. Research published during 2026 by astronomer Rodney Gomes proposed that Neptune's changing orientation may have emerged through gravity alone. As Triton's orbit gradually evolved from its original elongated path into the nearly circular one we observe today, the geometry between the Moon and its planet never remained fixed. The gravitational pull changed with it, creating an evolving tidal torque, meaning a twisting force produced by gravity that acts over immense spans of time. But this was no ordinary pull. As the orbital configuration continued to shift across hundreds of millions of years, the changing torque may have altered the way Neptune's spin axis slowly traced a circle through space. Astronomers call that motion precession, the gradual wobble of a rotating body's axis, much like the motion of a spinning top before it settles. According to the model, that wobble eventually matched a larger gravitational rhythm generated by the combined influence of the other planets, a resonance identified by the designation S8. Once that resonance formed, Neptune's axis could continue drifting toward a new orientation without any violent event. Gravity alone supplied the influence, applying an almost imperceptible adjustment year after year until immense stretches of time produced a measurable planetary tilt. Nothing dramatic appeared in a single orbit. Everything accumulated. If this interpretation proves correct, Triton's capture reshaped far more than Neptune's collection of moons. The moon altered the very angle at which the planet faces the sun, changing the pattern of its seasons and permanently influencing its relationship with the outer solar system. No other moon has been proposed to have transformed its planet in this remarkable way. We began by following a captured world, yet the deeper we travel into its history, the more we find a traveler powerful enough to leave its mark upon an entire planet. Every orbit Triton completes carries a consequence that cannot be undone. The very path that made this moon extraordinary also determines its distant future. Long after every geyser fades and every season passes, gravity will continue its patient work, drawing Triton toward the planet that captured it. Most large moons experience the opposite fate. In a typical prograde system, a moon travels around its planet in the same direction that the planet rotates. Earth and its moon provide the familiar example. The moon raises a tidal bulge on Earth, a slight stretching caused by gravity. Because Earth spins faster than the moon completes an orbit, that bulge is carried slightly ahead of the moon's position. The forward offset creates a gravitational pull that transfers rotational energy from Earth into the moon's orbit, nudging the moon farther away over time. Today, our moon continues to recede at roughly 3.8 centimeters each year. But Triton never joined Neptune's rotation. Its retrograde orbit reverses the entire geometry. The tidal bulge that Triton raises upon Neptune is dragged behind the moon instead of ahead of it. Rather than providing a forward pull, the displaced bulge acts as a brake. Orbital energy is gradually removed instead of added. Every circuit around Neptune becomes fractionally smaller than the last, although the change is far too small to notice within a human lifetime. The direction never changes. Physics offers no natural path that allows Triton to begin drifting outward while it continues moving opposite Neptune's rotation. The process unfolds across geological timescales, yet every completed orbit advances the same outcome. The captured moon continues a gradual inward spiral governed by the same tidal forces that once transformed its interior after capture. Eventually, another boundary awaits. Astronomers call it the Roche limit. The distance at which the difference in Neptune's gravitational pull across Triton's body becomes stronger than Triton's own gravity can resist. In simple terms, the near side feels a greater pull than the far side, and the moon can no longer remain intact as a single world. Material begins separating until the body is torn apart by the planet it has circled for billions of years. Exactly when that moment arrives remains uncertain. Earlier studies estimated that Triton might reach the Roche limit in about 3.6 billion years. More recent research, published during 2025, extended that estimate dramatically, suggesting a timescale of roughly 28 billion years, far exceeding the current age of the universe. The numbers continue to evolve as models improve, reflecting the complexity of long-term tidal interactions within the Neptune system. But one conclusion remains remarkably stable. Whether the final chapter unfolds billions or tens of billions of years from now, the direction never changes. Triton is moving inward, however gradually, because its retrograde orbit leaves no alternative. Among the large moons of our solar system, it stands alone. The same captured path that made Triton unlike every other great moon also became the sentence written into its future from the moment Neptune claimed it. Some endings arrive as a single impact. Others unfold across ages so vast that the destruction resembles another form of evolution. Triton's final chapter belongs to the second kind, beginning not with a collision, but with the crossing of an invisible gravitational boundary. The Roche limit is not a physical barrier waiting in space. It is a threshold defined by gravity itself. Once Triton moves inside that distance, Neptune's tidal forces, meaning the difference in gravitational pull between the moon's near side and far side, will steadily overcome the gravity holding the moon together. The change will not happen in an instant. It will begin slowly. Small deformations come first. The once rounded moon will stretch along the line pointing toward Neptune. Cracks will spread through layers of ice and rock that have remained connected for billions of years. Existing fractures may widen, while entirely new ones emerge, each responding to stresses that grow stronger with every completed orbit. Material near the surface could begin shifting long before the deeper interior finally yields to the relentless pull. But gravity does not pause. As the disruption continues, Triton faces two possible destinies. One scenario allows the moon to spiral deeply enough that it eventually collides with Neptune's upper atmosphere. Such an impact would involve a world measuring about 2,710 kilometers across, which is about 1,684 miles, releasing an extraordinary amount of energy within a geological instant. The event would reshape the planet's upper layers in ways no human civilization could ever witness directly. The second outcome appears more likely. Instead of remaining intact until impact, Triton may gradually break apart while still inside the Roche limit. Countless fragments of ice, rock, and frozen volatile materials would spread around Neptune, settling into a broad orbital disk. The moon would cease to exist as a single body, yet its material would continue circling the planet in a completely different form. The scale would be astonishing. Saturn's brilliant rings contain an estimated mass of roughly 15 quintillion kilograms. Triton alone possesses a mass of approximately 21 sextillion 400 quintillion kilograms, more than 1,000 times greater. If much of that material entered orbit as rings, Neptune could acquire one of the most extensive ring systems ever seen in the outer solar system, transforming the planet's appearance across millions of years. But even rings do not last forever. Saturn's famous rings are themselves thought to be comparatively young and temporary on cosmic timescales. they slowly lose material as countless particles drift into the planet below. A future ring system born from Triton would likely endure much longer because of its far greater mass, although it too would continue evolving under the influence of gravity. Nothing truly disappears. The plains shaped by ancient resurfacing, the frozen geyser fields, the layered interior, and the remarkable cantaloupe terrain would all become part of a luminous structure encircling Neptune. The world itself would be gone, yet every fragment would continue telling the same story, no longer as a moon, but as a ring of scattered light surrounding the planet that captured it so long ago. Imagine opening a book and discovering that well over half its pages remain unread. That is the position we occupy with Triton today. Nearly every remarkable landscape we have explored together belongs to only about 40% of the moon's visible surface, while the remainder still lies beyond close human observation. The reason is surprisingly ordinary. Voyager 2 had only one opportunity to cross the Neptune system. The geometry of that single encounter illuminated Triton's southern hemisphere, while much of the north remained in darkness. The spacecraft could not slow down, return, or wait for another season. When the flyby ended, our detailed view ended with it, leaving an enormous portion of this distant world effectively unmapped. That absence shapes every conclusion. We do not know whether the strange cantaloupe terrain extends across the unseen hemisphere. We do not know whether active geysers rise from northern latitudes or whether their distribution follows a completely different pattern. The northern polar cap may share the same mixture of frozen nitrogen, methane, and carbon dioxide found in the south, or it may preserve conditions that reveal an entirely different history of seasonal change. But the greatest uncertainty lies beneath the surface. The proposed subsurface ocean remains exactly that, a scientifically supported possibility rather than a confirmed discovery. Establishing its existence requires measurements that have never been collected at Triton. Gravity science, meaning precise tracking of a spacecraft's motion to reveal hidden variations in internal density, could expose structures buried deep below the ice. Magnetometry, the measurement of magnetic fields, could detect the signature expected from a conductive liquid layer. Seismology, the study of vibrations traveling through a planetary body, could reveal the arrangement of the hidden interior. None of these investigations has yet taken place. The geysers present another unanswered question. Are they powered primarily by sunlight warming translucent surface ice, or do they rise from heat generated within Triton itself? Each explanation predicts different eruption sites, seasonal behavior, and chemical composition. Voyager 2 gathered extraordinary observations, yet its brief visit could not collect the long-term evidence needed to distinguish between the competing ideas. Another mystery reaches even farther back. If Triton truly entered Neptune's domain as one member of a binary pair, then its lost companion may still travel somewhere within the distant population of icy bodies beyond Neptune. Astronomers continue searching for ways to reconstruct that ancient encounter, but no object has yet been confidently identified as the missing partner. None of these questions belongs to the realm of fantasy. Each can be answered through direct observation using instruments already understood by planetary scientists. We know what measurements are needed. We know how to perform them. The missing ingredient is simply another journey across the immense distance separating us from Neptune. Until that voyage begins, Triton remains one of the most thoroughly studied unknown worlds in the solar system, a place where every discovery stands beside an even larger space, waiting to be explored. Some of the greatest scientific discoveries begin as plans on paper rather than journeys through space. For Triton, that plan carried a single name: Triton, a mission designed to transform decades of careful inference into direct observation. The proposal arrived in 2019, led by planetary scientist Louise Proctor of the Lunar and Planetary Institute. The Trident team entered the National Aeronautics and Space Administration Discovery Program, a mission category built around ambitious science within a cost ceiling of about $500 million. Their destination was clear from the beginning. They wanted to return to Triton for the first time since Voyager 2 departed the Neptune system. But timing shaped every detail. The mission depended upon a rare alignment between Jupiter and Neptune, one that appears only about once every 13 years. By passing close to Jupiter, the spacecraft could steal a small portion of the giant planet's orbital energy through a gravity assist, meaning a carefully planned flyby that changes a spacecraft's speed and direction without consuming large amounts of fuel. That natural boost would shorten the voyage and make such a distant mission realistically achievable. The planned route reflected years of precise calculation. A launch during October of 2025 would have been followed by a Venus flyby in 2027. Additional passes by Earth during 2028 and 2031 would have refined the trajectory before the spacecraft reached Jupiter in 2032. Arrival at Neptune and Triton was planned for December of 2038, completing a journey lasting about 13 years. The encounter itself promised far more than a passing glance. Over roughly 13 days, Triton would have mapped the entire surface at modern resolution, measured Triton's magnetic environment, examined its atmosphere in detail, searched for evidence of a hidden ocean, and flown through active plumes to analyze the material escaping from below. Many of the questions we have followed throughout this journey could have received direct observational answers instead of remaining informed possibilities. But the mission never left the drawing board. During June of 2021, the National Aeronautics and Space Administration selected the Discovery 15 and Discovery 16 missions. The chosen spacecraft were Da Vinci Plus and Veritas, both focused on Venus. Triton was not selected, and with that decision, the carefully calculated launch opportunity began slipping away. The calendar kept moving. By 2025, the required launch window had closed. The favorable Jupiter and Neptune alignment that made the mission practical will not return in a similarly useful form for about 13 years. Scientists involved with Triton described the outcome as devastating because opportunities to reach the distant outer solar system depend upon these uncommon moments of celestial geometry. But the story has not ended. New ideas continue to emerge, including the Triton Ocean World Surveyor concept under the New Frontiers program and an ambitious design known as Triton Hopper, which would harvest frozen nitrogen from the surface to fuel repeated leaps across the moon. As of 2026, neither mission has received approval or funding, leaving Triton's greatest questions waiting for the spacecraft that has yet to begin its journey. Sometimes, the clearest way to understand a world is to find its closest relative. As we follow Triton's story toward its deeper meaning, another distant body comes into view, one that appears strangely familiar. That world is Pluto, and together they reveal how a single event can redirect an entire planetary history. Both began their existence within the Kuiper Belt, beyond the giant planets, where countless frozen worlds formed from the same ancient reservoir of ice and rock. Triton measures about 2,710 kilometers across, which is about 1,684 miles. Pluto measures about 2,377 kilometers across. That is nearly 1,477 miles. their sizes are remarkably close. Their similarities continue. Each possesses abundant nitrogen ice mixed with water ice and methane across its surface. Each supports a genuine nitrogen atmosphere, delicate but measurable. Each has a rocky interior beneath an icy exterior, making both denser than many other frozen bodies in the outer reaches of the solar system. For many years, astronomers even discussed whether Triton itself might be regarded as a dwarf planet had its history unfolded differently. But one world remained home. Pluto continued circling the Sun where it first formed, changing only through the gradual influence of sunlight, the slow release of internal radioactive heat, and the distant gravitational effects of Neptune. Triton followed a completely different path after capture, and every chapter since has been written under the influence of another world's gravity. When the New Horizons spacecraft reached Pluto during July of 2015, it overturned long-held expectations. Scientists found broad nitrogen plains, towering mountains built from water ice, possible cryovolcanic structures, and the vast heart-shaped region known as Tombaugh Regio. Pluto proved far more dynamic than many had imagined, yet important differences remained. Pluto does not display towering nitrogen geysers reaching toward space. Its landscape does not appear to erase impact craters across enormous regions with the same persistence. No terrain resembling Triton's remarkable cantaloupe landscape has been identified there. If Pluto shelters an ocean beneath its crust, current evidence suggests it receives far less internal energy than Triton, leaving that hidden sea under different conditions. But Triton experienced something Pluto never did. After its capture, immense tidal forces repeatedly flexed its interior over immense spans of time. Tidal forcing, meaning the continual squeezing and stretching caused by changing gravity, converted orbital energy into heat deep below the frozen crust. That energy likely reshaped the interior, renewed the surface, and perhaps sustained liquid water long after similar worlds had grown colder. The comparison strips away nearly every other variable. We see two neighboring products of the same distant birthplace, sharing composition, size, and ancient origin. One remained largely undisturbed. The other encountered Neptune and entered a completely different future. Everything that makes Triton appear unusually active, from its resurfaced plains to its potential hidden ocean, traces back to that single gravitational encounter. In reaching out to capture a wandering Kuiper Belt world, Neptune transformed an ordinary frozen traveler into one of the most extraordinary moons known in the solar system. The meaning of Triton becomes even clearer when we step back from Neptune and consider the broader map of the solar system. Viewed on its own, Triton seems extraordinary. Viewed alongside other hidden ocean worlds, it becomes part of a scientific revolution that has transformed how we think about where life-supporting environments might exist. When Voyager 2 explored the outer planets during the 1970s and 1980s, most scientists expected liquid water to exist only on rocky planets orbiting within the habitable zone, the region around a star where temperatures can allow water to remain liquid at the surface. Earth appeared to be the obvious example. The colder frontier seemed far less promising. But discovery changed that picture. Europa, the fourth largest moon of Jupiter, is now understood to conceal a global ocean beneath an ice shell estimated to be roughly 10 kilometers to 30 kilometers thick, which is about 6.2 miles to 18.6 miles. That immense body of water is believed to remain liquid because Jupiter's gravity continually flexes Europa's interior, generating heat through tidal deformation. Current estimates suggest Europa may contain more than twice the water found in all of Earth's oceans combined. Another surprise followed. Enceladus, a comparatively small moon of Saturn, possesses a confirmed subsurface ocean beneath its frozen crust. Jets rising from its southern polar region release water vapor, icy grains, and complex organic molecules into space. The Cassini spacecraft flew directly through those plumes and detected hydrogen, tiny silica particles, and organic compounds, observations consistent with hydrothermal activity, meaning heated water reacting with rock deep below the surface. The list continued growing. Ganymede appears to harbor a vast buried ocean beneath multiple layers of ice. Titan is also considered a strong ocean candidate. Even Ceres, the largest object within the asteroid belt, shows evidence that pockets of salty liquid, known as brines, may still survive below its surface. One discovery after another has expanded the inventory of places where liquid water may endure despite extreme distance from the sunday. But the pattern reaches even farther. Ocean worlds no longer appear to be unusual exceptions scattered across the solar system. They may represent one of its most widespread planetary environments, hidden beneath frozen shells instead of exposed beneath open skies. That realization changes where we search for habitable conditions and how we define worlds capable of remaining active across billions of years. Within that expanding family, Triton occupies a remarkable position. Here is a captured Kuiper Belt object orbiting about 4,500,000,000 kilometers from the Sun, which is about 2,796,000,000 miles. Yet, it may still preserve a deep ocean because capture itself supplied the tidal energy needed to sustain it. The very event that transformed Triton's history may also have prolonged its internal activity. If that hidden ocean truly exists, Triton broadens the implications far beyond Neptune. It suggests that distant Kuiper Belt worlds, long regarded as permanently frozen relics, could possess hidden reservoirs of liquid water as well. The farther we explore, the more the solar system reveals that warmth does not always come from sunlight, and living possibilities may arise in places once considered beyond imagination. At the far edge of the solar system, where sunlight has little strength left to offer, one of the most profound scientific questions still follows us. Could a world this distant provide conditions suitable for life? For Triton, this is no longer an idea reserved for imagination. It has become a serious topic of investigation within peer-reviewed scientific research. The question begins with three essential ingredients. Life as we presently understand it requires liquid water, a dependable source of chemical energy, and organic compounds capable of assembling into increasingly complex molecules. Triton appears capable of meeting each requirement, although every step still depends upon observations that have yet to be made directly. The first ingredient is liquid water. If the proposed subsurface ocean truly exists, it would remain liquid through a combination of internal radioactive heating and dissolved compounds that lower water's freezing point. More importantly, that ocean would likely rest directly upon a rocky interior. This arrangement places water in prolonged contact with rock, creating an environment remarkably similar to regions beneath Earth's deep oceans, where living organisms survive without receiving any energy from sunlight. But water alone accomplishes very little. Life also requires a continuing energy source capable of driving chemical reactions. Inside Triton, radioactive elements within the rocky core could generate enough heat to circulate water through fractures and porous stone. Hydrothermal circulation, meaning heated water moving through rock and exchanging minerals, creates chemical differences that microorganisms can exploit for energy. Entire ecosystems on Earth's ocean floor depend upon this process, thriving around hydrothermal vents despite existing in complete darkness. The third ingredient may already lie across Triton's frozen surface. Radiation acting upon nitrogen and methane produces complex organic substances known as tholins. These reddish materials are not living organisms, nor are they evidence that life has ever appeared. Instead, they represent complicated carbon based chemistry that may contribute to the collection of molecular ingredients from which prebiotic chemistry, meaning chemistry preceding life, can emerge under favorable conditions. But Triton offers something even more unusual. If its towering plumes originate from internal activity rather than surface heating alone, they may transport material upward from deep within the moon. A spacecraft passing through those eruptions could examine their chemistry directly without drilling through kilometers of ice, which is about miles of frozen crust separating the surface from the ocean below. That natural delivery system would provide an extraordinary opportunity to investigate an otherwise inaccessible environment. Few ocean world candidates present such a possibility. Scientists therefore approach Triton with careful optimism rather than certainty. No observation has demonstrated that organisms inhabit its hidden ocean. No instrument has detected biological activity beneath the ice. Those conclusions remain beyond present evidence. Yet neither has evidence ruled the possibility out. Published research increasingly frames Triton as a place where the known requirements for life may coexist beneath an icy shell. If liquid water, chemical energy, and organic compounds truly meet within its hidden interior, then one of the coldest worlds ever explored may also belong among the most scientifically compelling places to search for life beyond Earth. Few worlds preserve the memory of the early solar system as completely as Triton. Every circuit it makes around Neptune carries information from an age when planets wandered, smaller worlds were displaced, and gravity repeatedly rearranged the architecture we now take for granted. By following Triton's path, we are also tracing one of the oldest surviving records of planetary change. Planetary scientists often describe this era through the Nice model, one of the leading frameworks for explaining how the outer solar system evolved. According to this picture, Jupiter, Saturn, Uranus, and Neptune formed much closer together than they appear today. Over hundreds of millions of years, countless encounters with icy bodies gradually shifted their orbits outward, transforming the arrangement of the giant planets into the configuration you see today. But this migration unfolded through instability rather than calm progression. As the planets moved, their gravitational influences repeatedly aligned in ways that amplified one another. These resonances, meaning repeating gravitational patterns that strengthen over time, disturbed enormous populations of smaller bodies. Asteroids and icy objects were scattered across the solar system. Some fell inward toward the rocky planets. Others were thrown into distant space forever. A few encountered giant planets under exactly the right circumstances to become permanent companions instead of passing visitors. The scars of that age remain visible. The heavily cratered surfaces of the Moon, Mercury, and Mars preserve evidence of an intense interval of impacts that occurred around 4 billion years ago. This episode, commonly called the Late Heavy Bombardment, describes a comparatively brief period during which collisions increased dramatically across the inner solar system. While its exact timing and intensity continue to be investigated, the broader picture points toward an era when gravitational upheaval reshaped worlds on an enormous scale. But Triton records another consequence of the same restless epoch. Its capture required Neptune to pass through a region crowded with Kuiper Belt objects. increasing the likelihood that a binary pair would wander close enough for gravity to separate them. That simple fact provides valuable limits on where Neptune may have traveled and how rapidly its migration unfolded. Triton, therefore, becomes more than an unusual satellite. It becomes evidence that helps test competing reconstructions of the solar system's earliest history. Even today, its orbit continues to speak. Its backward motion, its inclination, meaning the angle of its orbit relative to Neptune's equator, and the shape of its path all preserve clues about the encounter that bound it to the giant planet. By recreating those orbital characteristics through detailed computer simulations, researchers can narrow the range of capture scenarios that remain physically possible. But the story reaches beyond a single moon. Triton functions as a natural calibration point, a real object against which theories of planetary migration can be measured. Long after the instability itself faded, this captured world continued circling Neptune, carrying within its orbit a durable record of one of the most transformative chapters in the history of our solar system. Time leaves different marks on different places. For Triton, the passing decades have brought almost no new observations at all. We are still looking, in remarkable detail, at a world glimpsed during a single encounter in 1989. Everything that followed has come from returning to the same collection of measurements with sharper tools and deeper questions. Since that flyby, the story of space exploration has expanded at an extraordinary pace. Humanity placed sophisticated rovers across the surface of Mars. The Cassini spacecraft spent 13 years exploring Saturn and its remarkable family of moons. New Horizons carried our reach to Pluto, revealing landscapes no one had imagined before its arrival. The James Webb Space Telescope began observing galaxies whose light started its journey near the beginning of cosmic history. Physicists even confirmed gravitational waves, faint distortions in space itself, produced by colliding black holes. But Neptune remained untouched. Across those same years, no spacecraft returned to its distant orbit. No approved mission revisited Triton, a world that overturned expectations with active geology, a remarkably unusual orbit, and the possibility of a hidden ocean has continued its path around Neptune without another close inspection. The questions accumulated, the observations did not. Yet science continued moving forward. Researchers repeatedly examined the Voyager 2 archive using increasingly sophisticated methods. Improved image processing uncovered details that earlier computers could not distinguish. Refined models of ice behavior reshaped interpretations of the strange cantaloupe terrain. New studies explored whether internal heat, rather than sunlight alone, could better explain the towering plumes. More recent gravitational modeling connected Triton's long orbital evolution with Neptune's present axial tilt, opening another avenue of investigation that did not exist when the flyby occurred. Each answer uncovered another layer. The remarkable pattern is that Triton science has advanced far beyond the age of its observations. Theoretical understanding has become richer, computational power has grown enormously, and laboratory experiments have improved our understanding of planetary ice and internal evolution. But every new interpretation still rests upon information gathered during a single brief visit more than 3 decades ago. That widening gap deserves attention. It does not exist because reaching Neptune violates the laws of physics. Mission designs have already been developed. Flight paths have been calculated. Scientific instruments capable of answering many of today's most important questions already exist. Engineers know how to build the spacecraft. Planetary scientists know what measurements are needed. But exploration always involves choices. When proposals compete for limited funding, even outstanding missions can remain on the ground. The Trident mission demonstrated exactly that reality. Its scientific goals received widespread respect, yet other compelling destinations ultimately received priority during the selection process. Triton's unanswered questions therefore remain unanswered, not through impossibility, but through decisions about where humanity directs its finite resources. As we continue our journey, you begin to see that the next chapter of Triton's story is waiting for observation rather than imagination. By now, you may notice that every remarkable feature of Triton connects to every other. Nothing stands alone. The deeper we have traveled into its history, the more each discovery has revealed itself as part of a single chain of events that began billions of years ago with one extraordinary encounter between a wandering world and a giant planet. It starts with the orbit. Large moons almost always travel around their planet in the same direction that the planet spins. Triton does the opposite. That backward path, known as a retrograde orbit, is far more than an unusual detail. It is permanent evidence that Triton did not originate beside Neptune. The laws of orbital motion leave almost no other explanation. From its very first revolution around Neptune, the history of another birthplace was preserved. But that distant birthplace explains everything that followed. Instead of forming beside Neptune, Triton began its existence in the Kuiper Belt, about 4,500,000,000 kilometers from the Sun, which is about 2,800,000,000 miles. There, it developed as a world closely resembling Pluto, with abundant nitrogen ice, water ice, methane, and a rock-rich interior, unlike the typical icy moons that formed around the giant planets. Its composition still reflects that earlier chapter of its existence. Capture changed its future completely. Scientists generally expect a captured moon to remain on a stretched, unstable orbit for immense spans of time. Triton no longer does. Its path around Neptune is remarkably circular because countless tidal interactions, meaning repeated gravitational stretching that converts orbital energy into heat, gradually reshaped both its orbit and its interior. The same process transformed the moon itself over hundreds of millions of years. But the consequences reached far beneath the surface. A world that should have remained frozen became unexpectedly active. At about minus 235 degrees Celsius, or minus 391 degrees Fahrenheit, Triton still displays evidence of erupting plumes, widespread resurfacing, remarkably young terrain, and the possibility of a hidden ocean beneath its icy crust. These characteristics overturn long-held expectations about what a distant moon can remain capable of after billions of years. The final consequence has not yet arrived. The same retrograde orbit that proves Triton's capture also determines its distant fate. Instead of drifting farther from Neptune, as many large moons gradually do, Triton continues an almost imperceptible inward journey. Over immense spans of time, that motion will eventually carry it across the Roche limit, the distance where tidal forces become stronger than the gravity holding the moon together. Whether it breaks apart into rings or ultimately reaches Neptune itself, the direction of its evolution is already established. Seen together, these discoveries form one uninterrupted narrative. The backward orbit reveals capture. Capture explains its unusual composition. Gravitational heating reshaped the orbit and awakened the interior. Geological activity emerged from that hidden energy. The same orbital geometry now guides Triton toward its eventual end. What appears at first to be 5 separate exceptions is, in truth, one continuous consequence of a single event that forever altered the destiny of a wandering world. Some stories eventually move beyond the measurements that first revealed them. Triton's does not leave science behind. Instead, it gently expands from it. After following billions of years of orbital evolution, geological change, and gravitational consequence, we arrive at a question that no instrument can fully resolve. Triton did not begin its existence beside Neptune. Unlike Earth's moon, which shares a common history with our planet stretching back to the earliest chapters of its formation, Triton originated somewhere far beyond Neptune's neighborhood. It formed in the Kuiper Belt, about 4,500,000,000 kilometers from the Sun, which is about 2,800,000,000 miles, alongside countless other icy worlds. It almost certainly traveled with a companion before gravity separated them forever during the encounter that changed both of their destinies. That separation became a beginning. Captured into an unfamiliar system, Triton entered an orbit it never would have chosen through its own motion. Neptune's gravity gradually altered every aspect of the world that arrived from the distant frontier. The orbit became nearly circular. The interior warmed through tidal forces, meaning repeated gravitational stretching that generated heat. The surface renewed itself. Layers of ice shifted. Hidden processes awakened beneath a frozen exterior. But time accomplished something even more profound. Triton has circled Neptune for billions of years. It has remained there longer than complex animal life has existed on Earth, longer than today's continents have occupied their present arrangement, longer than the Himalayas have risen above the surrounding landscape. Across those immense spans of time, Neptune ceased to be merely the planet that captured Triton. It became the environment that reshaped it into something entirely different from the world that first approached. Where, then, does belonging truly begin? Is it determined only by origin, or can it emerge through transformation across immense stretches of time? Triton's earliest history can never be erased. Its composition, its unusual orbit, and its distant birthplace remain written into its structure. Yet its present identity also cannot be separated from the planet that altered its orbit, stirred its interior, renewed its surface, and perhaps even sustained conditions that otherwise would never have existed. Both histories remain present. Planetary science does not attempt to answer questions about identity in the philosophical sense. Its purpose is different. It measures motion, reconstructs events, and explains physical change through observation and mathematics. Yet sometimes those same measurements naturally invite broader reflection. The equations describing orbital evolution also describe relationships that unfold over billions of years, gradually changing the nature of the worlds they govern. Perhaps that is why Triton remains so compelling. It reminds us that history and identity are not always identical ideas. A world can carry the memory of where it came from, while also becoming something profoundly shaped by where it has spent nearly all of its existence. Between those two truths, Triton continues its long journey around Neptune, preserving both stories at once. Every reconstruction of Triton's past eventually arrives at the same empty place. It is not a missing measurement or an unfinished calculation. It is another world, one that must once have shared Triton's journey, yet has vanished from every direct observation we can make today. The leading explanation for Triton's capture depends upon a binary system, meaning two worlds bound together by gravity as they traveled through the Kuiper Belt. During the close encounter with Neptune, that partnership could not survive. Gravity exchanged one future for another. Triton remained. Its companion departed. But departure does not tell us where. One possibility places the lost world within the scattered disk. a distant population of icy bodies occupying elongated and unstable paths far beyond Neptune. There, it could still circle the Sun today, following an orbit stretched across billions of kilometers, which is about billions of miles, gradually shaped by countless gravitational encounters over immense spans of time. It may already appear in astronomical catalogs under an ordinary designation, its deeper history completely hidden. Another possibility reaches even farther. If the encounter provided enough speed, the companion could have exceeded the Sun's escape velocity, the minimum speed required for an object to leave the solar system forever. In that case, it would have crossed into interstellar space, traveling at perhaps 1 or 2 kilometers each second, which is about zero point 0.6 or 1.2 miles each second. There would be no practical way to recover it. Every passing year would widen the distance by millions of kilometers, which is about millions of miles, until it became indistinguishable from the countless unseen bodies drifting between the stars. No observation has identified this missing companion. Scientists have attempted to reconstruct the ancient encounter through orbital modeling, tracing present motions backward across roughly 4,500,000,000 years. But each planetary interaction introduces tiny uncertainties, and those uncertainties accumulate until many possible histories remain consistent with the evidence. The mathematics narrows the possibilities. It does not reveal a final destination, yet the companion still occupies an essential place in the story. Without it, the binary capture model loses the mechanism that allows Triton to surrender enough orbital energy for Neptune to hold it permanently. The unseen world is therefore more than speculation. It is a gravitational inference, meaning a conclusion drawn because the observed motion of one object requires another object to have existed. We know its role through the consequences it left behind, even though its own path has faded beyond reconstruction. But perhaps that lingering absence is fitting. Triton's history began with a partnership that ended in an instant, leaving one world transformed and another carried beyond recognition. Somewhere, whether deep within the scattered disk or far outside the reach of the sun, a forgotten companion continues its endless voyage, preserving the other half of a story whose ending remains forever beyond our sight. When we stretch our view across the lifetime of the solar system, Triton no longer appears as a single frozen moon. It becomes a story unfolding over roughly 4,500,000,000 years, each chapter connected by gravity, chance, and extraordinary spans of time that no human life could ever witness in full. Its beginning lies in the Kuiper Belt, nearly 4,500,000,000 kilometers from the Sun, which is about 2,800,000,000 miles. There, amid countless icy worlds, Triton slowly gathered material through collisions and accretion, the gradual process by which small bodies merge into larger ones. Beside it traveled a companion, the two worlds bound together while circling the Sun in the same direction as the growing planets. They belonged to that distant frontier for only a brief moment in geological history. But the giant planets were still changing places. During the era of planetary migration, Neptune encountered the binary pair. Gravity reshaped every future in a single encounter. Triton surrendered orbital energy and became permanently bound to Neptune. Its companion disappeared into another path, leaving Triton alone around a planet it had never expected to orbit. Nothing remained unchanged. For hundreds of millions of years, perhaps even more than 1 billion years, tidal forces kneaded the interior whenever Triton swept around Neptune. Friction generated heat, ice softened, rock shifted, a possible ocean emerged beneath the frozen shell. Ancient landscapes disappeared beneath younger terrain, while the orbit gradually lost its elongated shape until it became almost perfectly circular. Every revolution recorded the memory of that capture. Then came stability. Across the following billions of years, Triton settled into the remarkable world we know today. It carried towering frozen cliffs, strange cantaloupe terrain, active plumes, and a surface that refused to grow old in the way scientists once expected. Around Neptune, it continued its long descent, the orbital distance shrinking by amounts too small to notice across a single lifetime, yet relentless across deep time. But the ending has already been written into the mathematics. Billions of years from now, perhaps even tens of billions, Triton will cross the Roche limit, the distance where Neptune's tidal forces become stronger than the moon's own gravity. The world will gradually come apart. Ice and rock will spread into countless fragments, each continuing the journey that Triton can no longer make as a single body. A moon will become a ring, transforming solid ground into a vast band of reflected sunlight circling the blue planet. The sun itself will not last forever, yet that future ring could remain long after our star has completed its own evolution, marking Neptune with the final expression of a world born in the distant Kuiper Belt, captured through cosmic chance, reshaped by billions of years, and ultimately returned to light, motion, and enduring orbital geometry. Some stories become clearer the farther away we stand from them. Triton's story does the opposite. The greater the span of time we consider, the more astonishing its persistence becomes, until ordinary human experience no longer offers useful comparisons, and we are left measuring existence against the history of the solar system itself. The capture occurred roughly 4,500,000,000 years ago. Those words are easy to pronounce, yet almost impossible to imagine. The oldest known animal fossils on Earth date back about 600 million years. Complex plants spread across the land roughly 450 million years ago. The extinction of the non-avian dinosaurs happened about 66 million years ago. Every kingdom, every city, every language, every discovery, every piece of recorded history belongs within only the most recent few thousand years. But Triton has remained in motion through all of it. For approximately 4,500,000,000 years, it has circled Neptune again and again, completing well over 200 billion revolutions. Every orbit carried it a fraction closer to the planet below, a change so slight that no observer could notice it across a lifetime, yet so persistent that deep time transforms tiny differences into an entirely different destiny. The universe works with remarkable patience. Worlds collide, orbits evolve, mountains rise and disappear, oceans freeze beneath ice, then perhaps remain liquid beneath the surface for ages beyond imagination. None of these processes require witnesses. They unfold according to gravity, heat, chemistry, and time, whether anyone is present to observe them or not. Human curiosity arrived very late in that sequence. But the story never paused while we caught up. Long before telescopes, before civilizations, before the first living creature climbed onto dry land, Triton had already become Neptune's captured companion. Its interior had begun changing. Its orbit had started to soften into a circle. Its surface was slowly rewritten across millions upon millions of years, each transformation building upon the last with extraordinary consistency. Even now, the process continues. The nitrogen plumes are believed to rise as high as 8 kilometers, which is about 5 miles, above the frozen surface before drifting back down. They emerge from a world near minus 235 degrees Celsius, or minus 391 degrees Fahrenheit, nearly 4,500,000,000 kilometers from the Sun, which is about 2,800,000,000 miles. As you listen, those distant eruptions may still be taking place, regardless of whether any spacecraft is nearby to record them. But that may be the most enduring lesson Triton offers us. The universe does not measure significance by attention, it measures change through time. Across billions of years, a wandering world was captured, transformed, and set upon a path toward an ending that has already begun, all while patiently continuing its journey through the darkness, one orbit after another. There is another way to look at Neptune, one that begins far beyond our own era. Instead of seeing the planet as it appears today, we can imagine it at the end of Triton's long journey, after billions upon billions of years have completed the work that gravity began almost as soon as the solar system formed. Today, Neptune possesses a delicate ring system, yet it remains remarkably faint. 5 principal rings circle the planet, although some appear as incomplete arcs sustained by the gravity of the small inner moon Galatea. From Earth, they are exceedingly difficult to observe, dim against the darkness that surrounds the outer reaches of the solar system. But this is only the beginning. As Triton continues its gradual inward migration, every orbit brings it imperceptibly nearer to Neptune. Eventually, it will cross the Roche limit, the distance where a planet's tidal forces become stronger than the gravity holding a moon together. At that boundary, Triton will no longer remain a single world. Ice, rock, frozen nitrogen, and complex organic material will separate and spread into an immense ring encircling the planet. Nothing comparable exists there now. The material of a world measuring about 2,710 kilometers across, which is about 1,684 miles, will become light arranged into vast orbital patterns. The same body that wandered through the Kuiper Belt, survived capture, reshaped its own interior, renewed its frozen surface, and perhaps sheltered a hidden ocean, will continue its story in an entirely different form. Its identity will change once more, although none of its substance will truly disappear. But Neptune itself will change with it. The distant blue planet, so often overlooked because of its immense separation from the Sun, may eventually possess one of the grandest ring systems in the solar system. What seems restrained today could become astonishing on a scale that future observers, if any remain, would struggle to compare with anything else circling our star. The timing hardly alters the outcome. Whether Triton reaches that final boundary in roughly 3,600,000,000 years, or after many billions more, gravity continues its patient work. The transformation unfolds at a pace that ignores civilizations, species, and even planets that may vanish long before the process concludes. Our own world is unlikely to witness that ending. Astronomers expect the Sun to expand into a red giant in approximately 5 billion years, dramatically changing the inner solar system and leaving Earth unable to support life as we know it. If curiosity survives beyond humanity, it may belong to descendants we cannot imagine, or to no observers at all. But the universe has never required an audience. Neptune's most magnificent appearance may arrive with no eyes to behold it, only the steady motion of countless shining fragments tracing perfect paths through the darkness, completing a story that began when a wandering world took one irreversible step too close to a giant planet. Some stories become clearer the farther away we stand from them. Triton's is one of those rare stories. When we gather every thread together, a single pattern emerges, one unlike any other known moon in the solar system. Every major moon circles its planet in the same direction that planet rotates, except one. Every captured world preserves the evidence of its violent arrival through an elongated orbit that never fully settles, except one. Every small, distant moon was once expected to become geologically inactive after its formation, except one. Every large captured object should have entered an established system and eventually become just another member of it. But one transformed everything around it, removing an earlier family of moons, reshaping its own interior through tidal forces, and continuing to send towering plumes above an icy landscape despite surface temperatures near minus 235 degrees Celsius or minus 391 degrees Fahrenheit. Every large moon seems destined to endure beside its planet for unimaginable spans of time, except one. Triton stands apart because each exception follows naturally from the same ancient encounter. A wandering world from the Kuiper Belt approached Neptune during the restless youth of the solar system. A binary partnership ended forever. One companion disappeared into an unknown future. The other remained, forever altered by capture, gravity, and time. Nothing about that sequence is symbolic. It is measurable. It is written into orbital motion, internal structure, surface geology, and the gradual loss of orbital energy that still continues today. Each revolution carries Triton fractionally closer to the planet that claimed it billions of years ago, continuing a process so gradual that no human lifetime could ever notice the change without careful calculation. But the change never stops. Beneath an icy crust, an unseen ocean may still endure. Above it, nitrogen eruptions may still rise several kilometers, which is about several miles, into the thin atmosphere before falling back across the frozen plains. The strange terrain continues to preserve clues that have challenged every new generation of planetary scientists who has examined the original observations. Yet our direct encounter with this remarkable world lasted only a handful of hours. That brief visit happened 37 years ago. Since then, our understanding has expanded through better models, stronger computers, and fresh ideas, while the images and measurements themselves have remained exactly the same. Triton continues its immense journey, whether we watch or not, revealing nothing new except through the patient language of physics. And so, for now, we remain separated by distance rather than curiosity. Somewhere beyond the familiar worlds, Triton continues its endless circuit around Neptune. The geysers may still be rising, the frozen ground may still be shifting. The orbit continues its gradual descent toward a future already written into gravity itself. Tonight, we can only follow that distant path with our imagination. Good night,